Welcome to a lesson with Dr. Powell. Let's take a look at finding the volume of a parallelepiped. That's a three-dimensional version of a parallelogram. So we have three different vectors. Maybe perhaps these in the plane where they exist form a parallelogram. These ones in the plane where they exist form a parallelogram. And if you put all the pieces together, all the shifting of the different sides, different places, and adding them up, we end up getting a parallelepiped. How do you find the volume of that thing? Let's just think about dot and cross product a little bit. Okay, so first of all, let's kind of get a plan. Call this U, V, and W, say. All right. If we took U cross V, we would get a vector that's orthogonal to the plane where U and V live. So it'd be along this line right here. The line where, okay, so it'd be orthogonal to it. So maybe, and it might be in this direction, but it also could be down there. But if it were down there, that would be okay too for our purposes. Okay. So, and let's just put the name of W right here next to where it is. And let's suppose that this vector right here would be U cross V. So what we have a few things happening. First off, we can find the height of this parallelepiped simply by finding the projection of W onto U cross V. So in other words, W, so dot, and then we're projecting onto U cross V. So to do that, you take that vector and divide by its length. Okay, this right here is the height of that parallelepiped. Now, all we need to do is multiply by the base. Okay, so the area of the base actually is really nice. It's easy to compute. I mean, we could use some projections and Pythagorean theorem and other things here if we just use dot product in order to do it, if we're clever. However, there is a nice fancy way of doing this by just using the cross product. If we refer back to the idea of quaternions, and if you multiply two things together, it creates a rotation, but it also creates an expansion by length as well. But the expansion by length and the rotation put together actually enable us to think of the cross product as being a projection onto an imaginary part, where it's kind of like this distance here in the rotation. And the dot product is like this distance if we just rotated, but we're actually expanding by the length of the base too. Well, that's amazing, because that's like multiplying this height by the base, and you get area. So actually the magnitude of the vector U cross V actually is the area of the base. Well, this makes this calculation nice. Those cancel. So the volume of the parallelepiped, to find the volume of the parallelepiped, is simply this dot product right here, W dot this cross product. So let's have an example. What if U were 1 to -3, V were 1, 1, 1, and W happened to be 6, 5, 2. Okay, let's find this volume. So first, we take a cross product between U and W. So let's do that over and write the result over here. So ignoring the first column, we have 2 minus a -3. So that would be 5. And then here, ignoring that column, we have 1 minus a -3. But then we, which would be 4, but then we switch the sign to be -4. And then, ignoring that column, you have 1 minus 2, which would be -1. So this is the cross product of u and v, and then we just dot it with w. 6, 5, 2. And let's take a dot product right there. And so we're going to end up getting, I'll just write it right here, 30 minus 20, so 30 minus 20 minus 2. So it looks like 8. So the volume of this parallelepiped is 8. Thanks for watching.